In the eternal darkness of the cosmos, there is something we cannot see. It has no shape. It makes no sound. It drifts silently between the stars like a ghost. It is a place where every law of physics surrenders, a place where time stands still and light vanishes. Hollywood once painted a picture of serenity, a majestic gargantua brooding in the shadows. But that silence was a lie. Because when this monster decides, it does not swallow in secret. It explodes. An energy so brilliant it dwarfs 100 billion suns combined. A perfect paradox between absolute darkness and the most radiant light. When a star crosses the tidal radius of a supermassive black hole, it does not simply vanish. Gravity stretches it into a thin stream of superheated plasma. Astrophysicists at MIT's Kavli Institute call this spaghettification, because sometimes only pasta can describe the violent end of a star. That shredded material does not disappear into silence. It collides with itself, superheats and erupts. And in that moment, the darkest object in the universe becomes the brightest, outshining 100 billion stars in its host galaxy. In early 2024, signal analysts at NASA Goddard Space Flight Center and astrophysicists at MIT's Kavli Institute, watching through the Hubble Space Telescope and TESS, caught something unexpected in event. At 2020 OCW, a black hole still radiating, still convulsing, months after the initial event, challenging our models of how long these celestial fires should burn. Which raises the question that will guide everything that follows. If the darkest thing in the universe can produce its most brilliant light, what else have we fundamentally misunderstood about the dark? To understand this scale, look back to 1994, when comet Shoemaker-Levy 9 slammed into Jupiter. The impact released energy equivalent to 300 million nuclear warheads, leaving Earth-sized scars on the gas giant. It was the most violent event our solar system had ever witnessed. And yet, a tidal disruption event makes Shoemaker-Levy 9 look like a lit match held up to a hurricane. The physicists and computational scientists at Syracuse University and the University of Zurich have calculated that a single TDE releases energy at a rate that would dwarf the Shoemaker-Levy impact by a factor that strains comprehension. Take every nuclear weapon ever manufactured on this planet, detonate them all simultaneously, and then do it again the following second, every single second, without pause, for 10,000 years. That is the order of magnitude of energy output when a star falls into a supermassive black hole. That is what lights up a galaxy from the inside. The destruction begins at the tidal radius, an invisible mathematical line where gravity overcomes the nuclear forces holding a star together. Once crossed, the star is stripped of its identity, drawn out into a river of fusion-hot plasma racing toward a canyon with 4 million times the mass of our Sun. The astrophysicists at MIT's Kavli Institute gave this process its now famous name, spaghettification. The star becomes pasta, long, superheated, X-ray emitting pasta stretched across a distance that would dwarf the diameter of our entire solar system. It is a scale of violence that puts our own existence into perspective. That star burned for billions of years, only to be unmade in a cosmic blink. If this occurred in our neighborhood, our atmosphere would be stripped away instantly, silencing our pale blue dot forever. We study this destruction to understand the forces that could just as easily erase us. But new simulations from Syracuse and Zurich have revealed the exact mechanism behind this brilliance. This debris doesn't simply vanish. It follows a coherent, eerie path, circling the black hole until it crashes back into itself. This self-intersection, this cosmic head-on collision, is the spark that ignites the flare we see across the void. This is the definitive answer to the mystery. It is not the black hole itself that shines, but this violent self-intersection that transforms a shredded star into the most brilliant beacon in the galaxy. The energy of that collision heats the material to temperatures measured in millions of degrees Celsius, and at those temperatures, the physics shifts entirely. The object erupts in X-rays, the most energetic photons on the electromagnetic spectrum, carrying so much energy that they punch straight through the dense clouds of interstellar gas and dust that would stop any other form of light cold. X-rays from a tidal disruption event travel across the universe essentially unimpeded, crossing galactic distances to arrive millions of years later at the sensors of our space-based observatories. That is the signal intercepted in T20200CW, not a single pulse of destruction, but a sustained emission that persisted long after standard models predicted the fire should have faded. It was the signature of a black hole struggling to process the immense influx of stellar debris, keeping the galaxy lit far longer than we ever thought possible. These cataclysms unfold in absolute silence. A star screams in X-rays, but only our robotic sensors can catch the flicker of a funeral that ended a billion years ago. We are simply witnesses to a ghost, but here is the deeper mystery these simulations are now unraveling. No two tidal disruption events look exactly alike. Some flare rapidly and fade within weeks. Others build slowly over months. Some burn brighter than every star in their host galaxy combined. And some, like the 2014 encounter between the dusty object G2 and Sagittarius A star at the center of our own Milky Way, produce almost nothing at all. This cosmic fizzle left astronomers baffled after years of anticipation. The answer, according to the computational teams at Syracuse and Zurich, lies not in the star itself, but in the black hole. Specifically, its spin. A rotating black hole drags space-time along with it, the way a spoon dragged through honey creates a swirling pattern in the surrounding fluid, and this frame dragging induces a phenomenon called nodal precession in the orbiting debris stream. This is where the physics of the black hole itself takes over. Its spin drags space-time, forcing the debris to wobble in a process called nodal precession. This determines the timing of the collision. If the spin and angle aren't perfect, the debris may never intersect at all, resulting in a cosmic fizzle instead of a galaxy-shaking flare. The secret to the light was hidden in the spin of the abyss all along. But we refuse to stay in the dark. The detectives charged with solving these cosmic crimes are the silent watchers we built with our own hands. In the high, thin air of the Chilean Andes, the Vera C. Rubin Observatory will soon open its eyes, transforming these rare tragedies into a vast library of knowledge. From their lonely orbits, Hubble and Tess act as our scouts, while the robotic sentinels of the Atlas network keep their patient vigil. It is a testament to human pride that a species so small, confined to a single rock, dares to build eyes capable of piercing the veil of eternity. Space is hard, and the universe hides its most spectacular secrets behind layers of distance and physics that took decades of accumulated human effort to decode. But the pattern is consistent. We built better eyes, and the universe gave us a T20200 CW, still burning years after it should have gone quiet. We built better computers, and the teams at Syracuse and Zurich gave us the first simulations capable of explaining why the spin of a black hole determines the light it produces when it shreds a star. Yet, this death is a metamorphosis. The heavy elements forged in that star's heart, the stardust in your veins, are recast and flung back into the void to become the seeds of new worlds. We are the universe's memory, and with every discovery, we move one step closer to the stars that made us.